Hi guys, welcome to lesson 3 of unit 1, Foundations of ESS. In this lesson we are going to talk about systems and models, and both of those concepts are really important in how we interpret scientific data that we're given and how we use information that we have to build our understanding of the world around us. So let's get started. The first thing that we need to do when we talk about systems and models is define what we mean by a system. Because a system can mean a lot of different things in science. So when we talk about a system, I'm going to get going with my pen again here. We are talking about an assemblage of parts and the relationships between them. So all of these things that are pictured on the left could be considered systems. The Earth, obviously, is an assemblage of many, many parts that are related in innumerate ways between the relationships of the big systems like the atmosphere to the hydrosphere, and the relationships of the small systems like the relationship between a city and its surrounding rural areas. On every level, the Earth has systems created from different assemblages of parts and the relationships of those parts to each other. So the Earth was a pretty complicated example to start with, but you can look at something more simple. And not that this is overly simple, but something like your cell phone can be considered a system. It's an assemblage of parts that all behave in relation to each other. There's an input of energy, there's an output of energy, and there is a clear function for what's supposed to happen when you use that system of your cell phone. The human body is another great example with tons of systems in it that you've probably studied already in middle school. The muscular system, the skeletal system, the nervous system, the optic system, all of those things work together to create the larger system known as your human body. So when you look at the organization scientifically of different systems sort of nestled within each other, you can see that in the body as a really good example. When we talk about systems, there are 3 different kinds of systems that we look at. We look at what we call an open system, and this is pretty common. Open systems exchange both matter and energy across boundaries. So you could be looking at the human body or the ocean, the Pacific Ocean, for example, or the Gulf of Mexico, or the city of New York. All of those are examples of open systems that exchange both matter and energy in many different forms between the outside and into the boundaries of the system. You can also look at what's called a closed system, and there aren't as many examples of closed systems. Closed systems are places that exchange energy but no matter. So that means that, for example, on the Earth, sun energy can come in and heat energy can leave, but we don't exchange any significant amount of matter with outer space. Earth is becoming a little bit more of an open system as we do more interplanetary exploration. But for now, we still consider Earth to be a closed system because we exchange a significant amount of energy but not very much matter across the boundaries of that system. Then, the last kind of system, and this is not that common, is what we call an isolated system. And in an isolated system, neither energy nor matter is exchanged across the boundary of the system. The only possible for now I shouldn't say possible, for now I should say the only isolated system we know of within the bounds of our current knowledge is the universe. As far as we know, our universe does not exchange energy or matter with any other system. There are some interesting theories around the multiverse and black holes and quantum physics that might one day allow us to create a theory about how the universe is actually not an isolated system. But for now, we consider the universe to not exchange energy or matter with anything else around it, making it an isolated system. So once those 3 kinds of systems make sense to you, you can think about how to show the pieces of each of those kinds of systems and the relationships between the pieces in different models. And when we talk about models in science, we are talking about a simplified description designed to show the workings of an object or a system. So you can have a model as a physical thing that exists. You can have a model as a diagram on a piece of paper, like the ones that you're looking at here for the water cycle and then for a predator-prey interaction. Or you can have what's called a software model, where you're using computer information to generate a model. Or you can even say that a math equation is a model. We have a lot of math equations in science and specifically in ecology that allow us to predict how a system is going to work. Like a good example is a Lincoln index allows us to predict how many organisms are in a population. We'll go over that in Unit 2. A Lincoln index is a good example of a mathematical equation that can be used as a model. So the pictures below should look familiar as models that you've studied previously in science. Some of you might also be familiar with the mathematical model of a Keeling curve, which is the carbon dioxide concentrations that were measured at Mauna Loa, and shows global carbon dioxide concentration going up, sort of like that, over the course of the last 100 or 140 years since the Industrial Revolution. Part of what we try to do in this class is create and label models. So let's look a little bit about how you can draw a diagram as a meaningful model. When you make a model in environmental systems and societies and in the IB curriculum in general, they're looking for some specific things. They're looking for storages represented as boxes or circles. So in this model, this would be a storage. They're looking for flows represented as arrows. So here you have arrows that are the inputs and outputs to your storage. They're looking at boundaries represented by lines. So you could draw a line around this whole thing and say that this is one model. You could also look at the line just around oceans in this water cycle and say that that's the boundary of the ocean. And then they're looking a little bit for you to be able to talk about processes, transfers, and transformations. So a transfer or a transformation is normally represented by an arrow. In a transfer, matter or energy changes location but not state. And in a transformation, energy or matter changes its state. So here we have one example of a transformation, evaporation happening, going from oceans, liquid water in the oceans, to gas in the atmosphere. So there's a transformation as well as a transfer happening at that point. There are also some places where just transfers are happening, like precipitation, water falling out of the sky to the land. The thickness of these arrows doesn't represent whether a transfer or a transformation is happening. What it represents is how much movement is going through that flow. So a thick arrow means that a lot of movement is going through that flow. Let me see if I can take some of this stuff off of here. And let's go forward so that we can keep talking a little bit more about models. The next thing we're going to look at is a design challenge. If you had to represent all of Earth as a model, with all of its storages and inputs and outputs, that would obviously be a really complicated thing to do. You'd probably want to start with a small landmass, try to nail down all of the storages, inputs, and outputs of various organic and inorganic compounds happening there, then look at how they interact with the body of water next to them, and then keep going to build out and get bigger and bigger and bigger in three-dimensional directions. So you're including water, land, air, geothermal storages, and all of the different interactions between those storages. In thinking about Earth as a model, it's important to again come back to this idea of the Gaia hypothesis, the idea that Earth is a living organism in which feedback mechanisms, and we'll get into feedback mechanisms a little bit more in the next class, maintain equilibrium, maintain balance in the system. So all of these different storages and inputs and outputs are connected to maintain an overall balance in the system. If you have a little bit of time, you might want to try to draw Earth as a model. It's a good exercise for this class, and it really makes you think about the different things that are involved in Earth as a model, and all of the different ways that the systems on Earth are connected to each other. For us, though, we are going to keep going and talk about a different kind of a model. So if this is a drawing design model, the idea of Earth as a model has been important enough that scientists actually tried to recreate a physical model, a Biosphere 2 model of a functioning ecosystem in the desert in Arizona. That functioning ecosystem was called Biosphere 2. This should link to a TED Talk video on your PowerPoint by one of the scientists that was involved in the Biosphere 2 project. If that doesn't link, you can look her up. She gave a great TED Talk. Her name is Jane Pointer. I'm just going to write it down here. Oh, I think I have her name a little backwards. Sorry about that. It's Pointner, and I think I'm saying that right. So Jane Pointner was one of 8 people that was voluntarily locked into this Biosphere 2 project in Arizona to try to create what we now call like a terraform project. It's the same thing that when we think about trying to go live on Mars, we're trying to build. And there's some really valuable lessons in creating this physical model of Biosphere 2 from tons of different computer models that have been created over the course of 20 years while it was being imagined and then invented. And the main lesson of Biosphere 2 is that it didn't work. Did not work. And the scientists that were involved in the project had to sort of abandon what they were trying to do there after 2 years because they were running really low on oxygen. And one thing that none of their modeling could account for was the idea that once they were actually in this structure, oxygen started to sink into the carbon of the buildings. And there was no model prediction for that. So I think that when you look at the importance of models in science, one thing that's significant to consider is no matter how carefully you create a computer model, you can face some difficulties in trying to turn that computer model into a reality. That's really all I have to say about systems and models for now. It's a topic that keeps coming back throughout the course, but let's take a look at the homework. So if you are following along in this textbook, and again, I do totally recommend the textbook, it's awesome, you want to read section 1.2 of the textbook, pages 17 to 25. And no matter whether you're doing the reading or not, you should be able to do this. Consider this picture and list 2 inputs, 2 outputs, and 2 storages of energy or matter that are taking place in this diagram of a geothermal power plant. This picture is from a Vox article called Why More and More Countries Are Taking an Interest in Geothermal Energy. And we will go over how to label this model in the review video. So take a few minutes to try and get this homework done. And when you're ready, I will see you in the next lesson. See you there.